In this lecture, we will talk about how we can handle deadlock conditions. So we'll try to look at several strategies that will help us mitigate deadlocks. So the first option that we have is to ensure that the system will never enter a deadlock state. And we can ensure this by using two options. One is deadlock prevention. We will talk about the strategies there. And the other one is to avoid deadlock. So deadlock avoidance. We are not going to go in to detail about deadlock avoidance, but essentially the idea is that you are going to find out what are all the uh, requests being going to be made by all the processes in your system ahead of time, and then allocate the resources ahead of time. So it is reliant on a priori information. So that's deadlock avoidance, and we are not going to go into the details over there, but we will talk about how to prevent deadlock. So that's when we are ensuring that it will never happen. The second option to handle deadlocks is to allow the system to enter a deadlock state. Then we can use an algorithm to detect whether a deadlock happened or not, and then we can use a recovery option. So let it happen, we will detect it, and then we will recover from it. The third option over here is to ignore the problem altogether. So pretend that deadlocks never occur in the system. This actually is used by most operating systems, including Unix and Windows. And the reason behind ignoring this problem, which the general purpose operating systems such as Unix and Windows are doing, the reason for that is that the cure is worse than the disease. Meaning, the two options that we have, well, the three options: prevention, avoidance, and detection and recovery. Those three options to handle deadlocks actually require uh, a bigger sacrifice from a user than simply restarting their computer once in a few days, or once in 1 year, for example. So the operating systems such as Unix and Windows allow the deadlock to happen, and they let the user reboot their system, as opposed to putting things in place to detect, recover, avoid, and prevent deadlocks from happening, because they give up a lot more things which are very useful for a user in that case. So the cure is worse than the disease, and hence these do not have that problem. So why are we studying in this course? Well, because we are designing operating systems, and we are designing the computer systems where we can learn from the possibilities of the deadlock when they happen, and the interaction between the processes and resources, um, and the concepts of allocation and request that are happening between the process and resources. We can learn from what are the potential pitfalls, and we can design those processes better. We can design the operating system better by knowing what are the potential problems once it is live. So that's why we are going to see how we can handle deadlocks. So let's go into deadlock prevention first. So this is prevention. We are going to see if we can do things that prevent the deadlock from happening. And we are doing that by restraining the ways a process can make a request for a resource. So in the previous lecture, we talked about four necessary conditions that should be held simultaneously in order for a deadlock to be guaranteed. Now, if we are able to break one of those conditions, if we are able to manage that one of those conditions will never be true, then we we definitely would have prevented the deadlock from happening. So, our goal is going to be to see here how we can break at least one of those four conditions. So first one was mutually exclusive. So one resource per process. So how can we break that? Well, try to have multiple resources per process. And the way we can do that is by having more than one instance of a resource type, or shareable resources. So if you have shareable resources, for example, read-only files, in that case, there is no mutual exclusion, which means that there are multiple instances of a resource type and the processes will not be very limited to what instance they need to use. So by having shareable resources, we will make sure that the mutual exclusion will not occur. Note here that some resources may not be able to be shareable. So they might always be non-shareable. So we can try to get mutual exclusion eliminated. However, we cannot do that completely. So it's not a very good way to prevent deadlock from happening. Next is, let us try to see if we can break the hold and wait. And we can break that condition by guaranteeing that whenever a process requests a resource, it does not hold any other resource. So process cannot request for resources while holding some other resource. So we can do this in a couple of ways, and both those ways are listed over here. The first one is require the process to request and be allocated all its resources before it begins execution. So tell me what you need, I will give you what you need, and then you work on it. So it's all, there's no waiting. The process will request all the resources it might need during its execution. The system allocates all those resources to the process, then the process begins execution. So it will break the hold and wait. However, the problem with that is poor resource utilization. What does that mean? That means that suppose we are using 4 resources, R1, R2, R3, R4, and R1 and R2 are, for example, say R1 is a hard drive, which takes a long time to access that memory type. In that case, even though I have my 4 resources blocked away for all that time, I'm not using all 4 all the time. I'm using maybe 1 at a time, maybe 2 at a time, but I'm not utilizing all those resources for the entire time I have held them for that process. So that leads to poor resource utilization, because those resources, say 4 of them, if they were being used by that process, they will not be able to use, they will not be able to be allocated to another process. My second option to break hold and wait is to allow process to request resources only when the process has none allocated to it. For example, if a particular process requires 4 resources, R1, R2, R3, R4, then at the beginning, suppose it doesn't have any allocated to it, then we can allocate it R1, then the process will use R1, release it, then it can request for another resource, maybe R2, R3. We will give it R2, R3, it will use it, release it. Then we can give it R4. So it is happening one at a time. So we are making sure that the process can request when it has none allocated to it. So the problem with that is, well, there are several problems with that. One is the changes that are made by the first step, are they going to be consistent with the second step? Are they going to be consistent with the third step? That consistency might be lost because we are doing this step by step. And in both these options, a common problem exists. What is that? That's the starvation, which means that if there is a particular resource which is always being used by some processes and is never going to be available, then if we do this, or the first option or the second option, then we are simply waiting for that high demand resource for a very long time, which means that our process will indefinitely be in that waiting state and never be able to progress. So that's called process starvation. So that's how we can break the hold and wait, and some problems associated with that. Next, let's try to look at how do we break the condition of no preemption. So we were not able to steal the resource from the process because of that no preemption condition. We were not able to do that. If such a condition holds true, that means that we are moving towards a deadlock state. So how do we break this no preemption? Well, allow preemption, right? So we are going to be able to allow the operating system to snatch its resources away. So when should we do that? Well, we can do that if a process that is holding some resources requests another resource that cannot be immediately allocated to it. If that happens, we ask the process to release all of its resources that are currently being used. So if you ask for more resources and I don't have it for you, then the operating system says, give up all your resources and we'll try some other time. So the process will be restarted only when it regains its old resources as well as the new ones that it is requesting. So once we have all the resources ready, then we can restart that process. So this is moving towards a preemptive a preemptive measure, preemptive condition, because we are essentially stopping the process voluntarily. So it's not like the process is voluntarily giving up the resource. The operating system is forcing it to give up all the resources. So that's how we break no preemption. We move towards preemption. The last one is, how do we break circular wait? Well, this is straightforward, because all we need to do is figure out what are the processes, what are the requests, and then impose a total ordering of all the resource types. So process 1 can use R1 and R2 for this amount of time. Then process 2 is going to use this resource and this resource for this amount of time. That all those assignments and requests can be scheduled ahead of time. So total ordering. And require that each process requests resources in an increasing order of enumeration. So by having a particular structure to this request and allocation mechanism between processes and resources, we can ensure that we can break circular wait condition. So if we are able to break any one of them, then the chances of the deadlock to happen go down. So we will be able to prevent it from happening. So that's as far as deadlock prevention is concerned. Now let's talk about deadlock detection. So in this case, we are going to allow bad things to happen. So we are going to allow the system to enter into the deadlock state. Then by using some sort of an algorithm, we are going to look at Banker's algorithm over here to specifically check for safety. It is also called a safety algorithm. So by using that algorithm, we can detect whether there is a deadlock or not. And the last step is, we'll see how we can recover from a deadlock. So allow it to go into deadlock, detect it, recover from it. So we'll take two examples. One is, what if our resource type is of single instance, so only one instance per resource type. And then we'll talk about the more general case of multiple or several instances for each resource type. So for the first one, we have a single instance for each resource type. In this case, what we draw or sketch is a wait for graph. So we are going to try to look at a wait for graph instead of a resource allocation graph. Actually, we can draw the resource allocation graph and then move on or convert it to a wait for graph. And that wait for graph directly tells us whether there is a deadlock or not. So we are going to see how we do that in just a bit. But in a wait for graph, our nodes or vertices are just processes. So we do not have any resources as vertices in this case, because they don't matter. We only have one instance per resource type. So it's redundant to sketch them into our wait for graph. And we are going to direct our edges from one process to another, indicating the wait for. So if the edge is going from pi to pj, what does that mean? That means that ith process waits for jth process. So that means that jth process is holding some resources and ith process is waiting for jth process to finish so that it can use that resource. So if p sub ith process is waiting for jth process, That's when we direct that edge from Pi to Pj. Periodically, we are going to invoke this algorithm that searches for a cycle in the graph. And in this case, you only have one instance per resource type, which means that if there is a cycle that exists, then for sure we are going to have a deadlock. An algorithm that detects a cycle in this wait for graph requires an order of n squared operations, where n is the number of vertices in the graph. In this case, all our vertices are corresponding to the processes. So by that, we can get an idea or estimate about the number of operations required to detect a cycle or a deadlock. So we have two graphs over here. The one on the left is a resource allocation graph, and on the right is the corresponding wait for graph. So let's talk about how we go from the resource allocation graph, where we have processes and resource types, to the wait for graph, where we only have processes. So for example, over here, let's take an example of R2 to P1 to R1. So resource type 2 has been assigned to process 1, and process 1 is waiting for resource type 1. How are we sketching all of that? Actually, let's do it between processes. So let's start with P1, go to P2. Process P1 is requesting for resource type R1, but resource type R1 is assigned to P2. That means P1 is waiting for P2, and that is indicated over here by that horizontal line right there. Similarly, P2 is waiting for R3, R3 assigned to P4, hence P2 waits for P4, indicated by that. Similarly, we have P2 waiting for P3 because of R4, P3 waiting for P4 because of R5, P2 waiting for P4 because of R5, and lastly P4 waiting for P1 because of R2. So that's how we move from a resource allocation graph to a wait for graph. Now once we do that, only for the single instance of a per resource type, we can do this. And once we do that, we check for a cycle. So it turns out we have actually two cycles in this graph. So one is P4, P1, P2, P4. That's one cycle, and the second cycle is P4, P1, P2, P3, P4. So we have two cycles, and for sure we have a deadlock state here. Now the more general case is several instances of a resource type. So in this case, the algorithm is going to be a little bit more complex. We are going to have to maintain vectors and matrices of processes and requests. So let's work through some examples to get a good idea about the detection algorithm. So before we get into the numbers, let's define certain vectors or matrices that we will need that will help us work through the algorithm. So the first one we have is the available vector. So available is a vector of length m, where m is the number of resource types. So m indicates the number of available resources of each type. So when we take a look at some examples, you will see what that m is. So suppose you have three resource types, R1, R2, R3, then m would be 3, for example. But that's just a vector. What it contains is the number of instances of R1, R2, R3 that are available. Next, allocation. Allocation is a matrix. The number of rows in the matrix are n, corresponding to the number of processes. M is the number of resource types, R1, R2, R3, like we said earlier. So it's a matrix of n by m, which defines the number of resources of each type currently allocated or assigned to each process, where number of row n, each row is corresponding to each process, each column is corresponding to each resource type. It's a matrix. Request is also the same size matrix, n by m, n rows, m columns. But now instead of allocation, it is indicating requests. So this indicates the current request of each process. So suppose if request at row number I, column number j is k, that means that p sub I, process number is I, is requesting k more instances of resource type rj. So I is the process number, j is the resource type number, k is the number of instances it is requesting. This matrix is also n by m, number of processes by number of resource types. Now in the detection algorithm, we have 4 steps, and these are relatively very straightforward steps. However, they become relatively straightforward once we work through an example, and we'll do that. For now, we will just talk about them a little bit, but when we really get to the example, numerical example, that's when we can actually understand this better. This algorithm falls under the category of banker's algorithm, but here we are only using it to check for safety. So to see if we are going to have a deadlock or no deadlock. So we are just going to do that. We can do other things with that algorithm, but we are only checking for safety. So step 1 is we are going to define vectors work and finish. We are going to define these 2 vectors, and we are going to set their lengths to be m, number of resource types, and n, number of processes respectively. So work and finish, new vectors, their lengths are m and n respectively. And so the step 1 is essentially initialize. How are we going to initialize it? We are going to take the work vector and essentially initialize it to be the same value as the available vector. We talked about what that available vector is. It is telling you which resource type is available, number of instances of each resource type that are available. So we are going to say work equals available first. Then we are going to say finish of I. So I is for each process. For each process, we are going to say finish as false when the allocation for that process is equal to not equal to 0. That means that some resources allocation is what are the resources that are assigned to a particular process. So if the allocation is non-zero, which means that there are some resources that are assigned to a particular process, it has not finished, which means I'm going to say that particular process, that index I of that finish vector is false. Otherwise, if the allocation for that process I is 0, that means that no resources are allocated to it, and we can say finish of that particular index I corresponding to that process is true. So once we in most cases we will just set all of them false, give a quick glance at allocation. If the allocation values for each particular process is non-zero, then we directly set them to false, which is often the case. So that's initializing step. Step 2 is find an index I, or find a process such that both finish of I equals false. That means that the process is currently holding some resources. It has not finished. That has to be true. Then whatever resource instances it is requesting has to be less than whatever is available. So if we are able to work on that process, then we are trying to find that particular index I. There could be multiple options at any given time. We are trying to find one of them. And if there's no such I that exists, then we go to step 4, which is essentially, okay, I'm done. I'm going to release all the resources. But at the beginning of an example, this is not going to be the case. Over here, we are going to have finish I to be false, and hopefully we have we are requesting for something less than what is available. Because if we request for something more than what is available, we are directly into the deadlock state. So that's step 2. Next is whatever process we checked for. Once we found out the process which we can work on, we work on it and we finish it. Then we once that process is done, it is going to release its resources. So we are going to update our work vector by simply saying work equals work plus allocation for that particular process I. It was allocated certain resources, now it's done, so we can use it to do some other process. So we are going to update the work vector. Next, because we just finished it, we are going to make that particular index I for that process, the finish vector, we are going to make that true. Then we go back to step 2, which means that we are going to continuously do that for all the indices I, so for all the processes. But it at any time, if we are requesting for something that we don't have available, we come to the step 4, which is essentially saying that we will be in a deadlock state. So if finish of I equals false for some I between 1 and n, whatever n processes that we have, if for any process we were not able to finish, then the system is in the deadlock state. Moreover, if finish of I equals false, then that particular process, p sub I, is deadlocked. So by going through this, if we are able to go through step 2 and step 3 for all the processes, then we are good. If we land in step 4, then we have problems. An algorithm that this particular algorithm will require big O order of m times n squared operations to detect whether the system is in the deadlock state or not. So let's actually work through this with an example. So the example over here is there are 5 processes, P0 through P4. As you can see over here, they are all highlighted in blue all the way on the left. There are 3 resource types, ABC. They are highlighted in yellow here. A has 7 instances, B has 2 instances, and C has 6 instances. And at a particular time, T0, this is the snapshot of the allocation matrix, the request matrix, the available vector. We are going to work on the 2 things over here, which is the work vector and the finish vector, in just a bit, because that is part of step 1. But at T0, let's see, how do we read this? One instance of resource type B is allocated to P0. 3 instances of resource type C are allocated or assigned to process 2, and so on. And at T0, process 1 is requesting for 2 more instances of resource type C, and so on. What is available? Oh, nothing is available. So our work is available. So the first thing that step 1 was what? Step 1 is work is available. So right now we don't have any resource types, any instances of any resource type. Let's see if we can initialize finish. Well, to do that, we have to check the allocation matrix. Is any allocation matrix equal to 0? Well, P0 is 0, 1, 0. No. P1 is 2, 0, 0, 3, 0, 3, 2, 1, 1, 0, 0, 2. So none of them is 0, 0, 0. So we are going to say false for here and here and here and here and here. So all of them need to be worked on. Next, we are going to do step 2. Step 2 is find the process that can finish. So let us see. Process 0 is requesting for nothing, 0, 0, 0. That means that we don't need to do anything, it can finish because request is less than or equal to available, less than or equal to work. So we can finish P0, no problem. So once we finish P0, we are going to have to go to step 3. Step 3 is once P0 finishes, we are going to do 2 things. One is update work. It was allocated 0, 1, 0. So we are going to update work with 0, 1, 0 because it got done. And because it got done, we are going to say finish is going to become true for that particular process P0. Next, we are going to go back to step 2. Step 2 is check for another process that can finish. Right now we have available 010. Let's see, P2 doesn't require anything. 000. In fact, we could have done this first, but it's okay, we did P0 first. P2 is next. It could finish. 000 is less than or equal to 010, so that's fine. So we'll work on P2. P2 will finish. It will release 3 instances of A and 3 instances of C, which will make work update to 313. And because P2 finished, we are going to make that true. Next, we will go and see which we can work on next. Can we work on P1? Sure, we can work on P1 because 202 is less than 313. So P1 can finish next. So when P1 finishes, we are going to again update work with add 2 here and add 2 here. Then P1 finished. Notice over here we could have chosen a different order. That's completely okay. What else is remaining? P3 is remaining. Can P3 finish? Yes, it requires 100. We have 515, so it can finish. And once it finishes, we are going to update. Okay. I think I made an error here. Once P1 finishes, it will add 200. So this needs to go back to 3 because it is allocated 200. It released 200. That becomes P2. Yes, 5, 1, and 3. Right. Okay, so we had finished. Let's see. P1, P2, P3, P0, P1, P2. Let's see if we can work on P3. P3 can, yes, P3 requires 100. We have 511. So P3 can finish. Once it finishes, it will release 211, which will be added to work. So 2 will make this 7. This will go up by 1, and that guy will go up by 1 more. So we have got that, and P3 was finished. So that becomes true. The last process is P4, 002. They're all less than 724. So P4 can finish and it will release 002 here. So that is easy. That is going to become 6 now, and that will become true next. So let's see here. Okay. So all the processes we're able to finish in this case. That means no deadlock was there, and that's how you would work through this example. At the end, we have the work vector with all the available 7, 2, and 6 instances of A, B, and C that we had originally. Okay, so I hope that was helpful. Let's move on to a slightly different situation where a deadlock is there. So let's suppose that P2 requests an additional instance of type C. So at the beginning, if P2 was requesting for one more type of instance of C, what would happen? So if I go back here and check what would happen if this was the case. C was 1 here at P2. So essentially I can go back and change this. P2 is requesting for one more resource type. I have updated that right there. What would happen then? To quickly do this, I'm going to go back to my original state. All of these guys were false. So that essentially was my starting point. I have initialized work and finish. What would happen now? Well, P0 can finish, no problem, because it is requesting for 000. Once it finishes, it will release one instance of type B. So we have 010. But now what is going to happen? Well, this will be true. But at this time, all our processes are requesting for something that we don't have. 202, we don't have that. 001, we don't have that. We cannot finish any one of the process. So right now we finished P0, and for P1, P2, P3, P4 we are in the deadlock state. So that's exactly what the example is suggesting, that if you have that particular change in the request matrix, the state of the system is going to be deadlocked. So we were able to reclaim the resources held by P0 only, but this was insufficient to fulfill the other processes' requests. So that means that there is a deadlock that exists, consisting of P1, P2, P3, and P4 processes. P0 was, however, able to finish. Okay, so I hope that example on detection algorithm was comprehensive, and you were able to get a good idea about how to work through the problems in this case. Next, let's talk about the usage of the detection algorithm. So when do you use it? How often do you invoke this detection algorithm? Both of those questions depend on the answers to how often a deadlock is likely to occur. So if there is a very frequent occurrence of deadlock, then you would want to invoke the detection algorithm frequently. And the other question that you have to answer is how many processes will be affected by deadlock when it occurs. So if there are a lot of processes that are getting affected by this, you may want to increase the frequency and the time at which you invoke it. If there are only few processes, then you might have to adjust your intervals accordingly. Notice that once everything goes into a deadlock state, and if it stays there for a long time waiting for resource allocation, the number of processes that are involved in that will slowly increase, because more and more resources will come in and start waiting for those resources that are held up. So it is not a good thing to happen, and if we stay there for longer time, we will have more processes that will get deadlocked. So invoking the detection algorithm, we may want to do it for every resource request. So every time a process requests for a resource, we may want to invoke the detection algorithm. The problem with that is that this is going to add up a lot of computation time overhead. So every time request, that happens a lot of time. So we are going to do this switching or detection algorithm where the number of operations are m times n squared. So that's a lot of operations. So a lot of computation time overhead for that solution. So instead we can perhaps do this detection algorithm at a defined interval. Maybe once every hour when the CPU utilization goes below 40%. So if a system is in the deadlock state, then the CPU utilization will go down because the number of processes that are able to finish in a given amount of time go down. So if that number goes below 40%, we may be interested on invoking the detection algorithm to detect whether there is a deadlock or not. But we still have to fix it. We still have to recover from it. So let's see that in a bit. So how do you recover from a deadlock? Well, there are two options. The first one is process termination. Let us kill some processes, maybe all of them, about all deadlock processes. That's a terrible option, because that option essentially says I have worked on several processes. I have maybe done 50% of the work there, 30% of the work there, 90% of the work for a different process. I'm going to kill or abort all the deadlock processes. That's a pretty bad option, but that is an option that falls under the category of process termination. A slightly better option, actually a lot better option, is to abort one process at a time until the deadlock cycle is eliminated. Now, we are going to choose a particular victim process and abort that until we eliminate deadlock cycle. Now there are several questions that are related to that particular choice. In which order should we choose to abort? Should we abort the resource, the process that has higher priority versus lower priority? How long the process has computed? So if it reached 90% of its computation, should we terminate that? Or should we terminate a process that is just starting up and it has progressed 10%? How about the resources the process is using? Should we terminate the process that is using only one resource or 10 resources? How should we do this? Depending on the resources process needs to complete. So should we terminate the process that requires more resources versus less requests in the future? um, how many processes will need to be terminated? Because of terminating one process, does it have an effect of on other processes that will need to be terminated as well? um, and is the process interactive, which means that we are going to go back and forth between the user and the process, or is it a batch process where there is no interaction? So depending on the answers to all these questions, or some of them at least, that's going to help us figure out which process to select as a victim process and the order in which we do this. So that was process termination. The next one is resource preemption. Essentially, snatch the resource from the process. So again, we are trying to select a victim here, but we are going to select a victim such that we minimize the cost, which means that, again, the same sort of questions that we answered earlier, we are going to choose a process that is essentially high priority, or it has only a few resources that it is using right now, and it's very low cost, meaning not too many other processes are going to be affected because of its elimination. So it's a very important and a crucial step, but we do need to select a victim to preempt resources from it. So once we have that victim, we are going to do a rollback, which means that in order to return to a safe state, so we do this when we are in the unsafe state of deadlock. To return to the safe state, we can take away resources from the process and restart the process from the particular state where we go back. So essentially, if we have progressed, say we wanted R1, we got R1, we wanted R2, we got R2, and once we got R2, we went into this deadlock state. We are going to roll back to the previous safe state and then restart the process. So that's the second way to do this. The third way is the starvation. So starvation will happen if uh, a process is never able to complete. So same process may always be picked as a victim, uh, and that will ensure that we will never be able to make progress on that victim. So if there is a particular process based on our criteria to establish minimum cost, we keep selecting the same process again and again, then that process will never be able to complete. So that will lead to process starvation. Okay, so I believe you guys are ready for activity 23. That's it for the deadlock.